G'day and welcome to the second of my 3 videos describing how to graph rational functions. Now if you saw my last video, you'll know that rational functions are in fact functions in the form of a ratio, why they're called rational functions, a ratio or a fraction with one polynomial divided by another polynomial. You'll also know that they come in 3 varieties, at least we've categorised them into 3 varieties. Type 1 was where the top polynomial was of a lesser degree or less powerful than the bottom one, and we looked at those in the previous video. In this video we're going to examine polynomials that are of the same degree, that is, their highest power is the same in both cases. So they're both linear functions with like 2x minus 3 and x plus 1, or they're both quadratics with x squareds, or they're both cubics or both quartics or something like that, but they must match to be considered a type 2. And type 3, which will be in the next video, will have the more powerful function on the bottom. Now the reason we categorise them this way is that each category behaves in a particular way. And what's particularly common in this one is this feature. I'm going to give an example. If we have, I'll make it simple, let's have a linear function like 2x plus 5 over x minus 1. If we were going to graph this, and we were interested in finding the horizontal asymptote, because these are like, they behave sort of like hyperbole, and if there's going to be some asymptote somewhere that the curve will tend towards as we get out to very large values of x, one way to find it is to find this. The limit as x tends to infinity of 2x plus 5 over x minus 1. And the way we do that is we find the highest power, in this case it's simply x, and we divide each part of the expression by x. So we've got 4 bits here, and every one of those bits gets divided by x, and you can see that this is 2x over x is simply 2. Can't improve on 5 on x, so we'll leave that alone. X over x is worth 1, and 1 over x we leave untouched. And I think you can see that when we take the limit as x goes to infinity, anything that is a fraction with an x or an x squared or an x cubed on the bottom, in this case the ones with the x's, will tend to 0. That is, as x becomes monstrously large, the fraction becomes incredibly small. And as x tends to infinity, this fraction becomes so tiny it tends to 0. So this limit is going to be 2 take away 0 over 1 minus 0, which is 2. Now the shortcut for looking at it is to simply look at the ratio of the coefficients of x on the top and the bottom, 2 over 1. And that's the shortcut. So you should be able to look at these and find the the horizontal asymptote quite easily. So here y would equal 2 would be the asymptote. Now I'm going to recommend something a little different from this. I do recommend, of course, that you know how to take these limits. But here's another way of finding the asymptote, the horizontal asymptote for this particular function. And I want to discuss it first before we go on and do any graphing. And it's simply to do this. We'll just ignore this for the moment, but it's to perform the actual division. So off on the side of my page, I'm going to divide x minus 1 into 2x plus 5. Now x goes into 2x twice, so I'll put the 2 in the units column. 2 times x is 2x. 2 times negative 1 is negative 2. I perform my subtraction. That minus that is 0. And 5 minus minus 2 is 5 plus 2 is 7. So this fraction, this division, turns out to be worth 2 with a remainder of 7. And that remainder of 7 still has to be divided by the x minus 1. Now the reason I recommend doing this division is that once we have this equation, we can subtract 2 from both sides. Now I've really not given myself room here. I'm quite frustrated by this. Let's just create it in a very clumsy way. And if I subtract 2 from both sides, I get y minus 2 equals 7 over x minus 1. And it's this form that tells me that one asymptote is where x equals 1 and another asymptote is where y equals 2. And in this form it allows me to examine this numerator, which can give me more information about the graph. So the division is actually very, very useful, and you'll see me take steps in that direction with a number of these functions. Now, this has been a long introduction, but I want you to understand the principles that we're looking at here. And as I show you some of the graphing techniques, you will, I think, appreciate why this division is so useful. So let's have a look at a few functions. I think I've got about half a dozen we're going to discuss. Well, here's our first one. You might recognise it as one we discussed. And what do we end up with? I think we ended up with y minus 2 was equal to 7 over x minus 1 from memory. This is after we performed the division. Now, let's analyse this. Okay, job number 1, horizontal asymptote. You could tell from here the coefficients of the x's that y equals 2 would be the horizontal asymptote, but it's also quite easy to see here that y equals 2 would give me a 0 here, and it's impossible for 0 to equal 7 over some number. So y equals 2 is going to be our horizontal asymptote. We draw it in. That's 1. Our vertical asymptote. We only have 1 in the fraction. When x is worth 1, we would end up dividing by 0, and we can't have that. That's undefined. So x equals 1 is our vertical asymptote. What's its nature? Well, it's a simple asymptote. There's no square or cube or fourth power on this. So we have two quite simple orthogonal asymptotes. Next question, are there any intercepts? Well, when x is, let's look in here, when x is worth 0, y is worth negative 5. 0, negative 5. There we go. So the curve must pass through that point. If y is 0, we actually get a value for x that would make this 0. And that's the value of x that would make that 0. X would have to be minus 2.5. So minus, there's 0, 1, 2, 2.5. So the curve must apparently go through there. Now, it's interesting here, it would look like we have a change of sign, S-I-G-N, occurring, but when we see it in this form, we see this is not the case. We have actually a very simple hyperbolic form, or form for the hyperbola. Next question. With a positive coefficient of x and a positive coefficient of y and a positive constant, we would expect that the initial part of our curve will be in the upper right hand corner, and basically that's enough for us to perform our graph our function. It will be in here somewhere, and then down in here it'll be in this position. If I was to point out that this multiplied by this would have to give 7, you can start to see why from the centre here, if I go back 1, I go down 7. 1, 2, 3, 4, 5, 6, 7. Or I go back 1, 2, 3, 4, 5, 6, 7 and down 1. So I've probably drawn that a little bit high there. This point here is back 1, 2, 3 and a half, and it's down 2. So minus 2 times 3 and a half, or minus 2, 3 and a half times minus 2 would give us plus 7 as well. And we would have the corresponding calculations up here. So we go up 7 and up 1, or across 1 and up 7, and so forth. But that's enough to draw a fairly decent graph of this particular function. And we start off with a fairly simple one. Notice the difference with these type 2 functions. They still have a horizontal asymptote. All of them do, but it's no longer on the x-axis. It'll be in some other location. So, that's a nice gentle start. Let's look at the next one. Now, this particular rational function has got a quadratic equation, or a quadratic expression for both the numerator and denominator. I think you can see that the coefficient of this is 1 and the coefficient of this is 1, so y equals 1 will be our horizontal asymptote. Now we could demonstrate that by taking the limit of this expression as x tends to plus infinity or minus infinity, but I'm going to want us to perform that division. I'll perform it down the bottom here where it's moderately out of the road. Now, being a quadratic, I'm going to write it x squared minus 4x plus nothing. Remember, we must have a units column and an x column and an x squared column. And up on the top, we've got x squared and no x's and a minus 4. Well, x squared into x squared only goes once, and we put the 1 in the units column. And 1 times all of this will be x squared minus 4x plus 0. And we perform our subtraction. X squared minus x squared is 0, as we expected. 0x's minus 4x is plus 4x. Remember that two minuses make a plus. And minus 4 minus 0 is still minus 4. So this one is telling us that y is equal to 1 with this remainder. So I'm going to put plus 4x minus 4 still divided by the x squared minus 4x. Now before we do any graphing, I want to go another step further. We're going to bring the 1 over here, and we got y minus 1 equals this. Now I'm going to factorise. On the top we've got 4 as a common factor, leaving x minus 1. And on the bottom, x is a common factor, leaving x minus 4. Now this is the form that I find most useful for graphing. What does it tell us? Well, first of all, it tells us the horizontal asymptote is where y equals 1. Well, we sort of knew that anyway, but it's just another way of seeing that. It tells us we have two vertical asymptotes. Well, we could have seen this up here too. One asymptote is where x is 0, so it's going to be right here on the y-axis. And the other one is going to be where x is worth 4. So we have an asymptote here. And they're both, in fact all three of them are normal asymptotes. So we've found our asymptotes and we know their nature. Let's look for intercepts. Well, when x is 0, we get a 0 on the bottom. 0 minus 4 times 0 is just 0. Doesn't matter what's on the top, but it's undefined. So there's no value on x equals 0, and we can see that anyway because it's an asymptote. So we don't expect to have any crossover point. What if y was 0? Is there any x value that would give us a y value of 0? Well, in fact, there are two. If we looked at this first expression, this is x minus 2 times x plus 2. Isn't it? Difference between squares over x times x minus 4. So in this form, it's telling us that when x is worth 2, y will be worth 0. When x is minus 2, y will be worth 0. So when x is 2, y will be worth 0. Minus 2, 0. Now, those points are useful to know. What else is useful to know? Well, this is one thing that this expression doesn't give that this one does. Because if we look at the top here, I should use a different colour. If we look at this expression on the top, we notice that we've got a problem or something significant occurs when x is worth 1. This looks like our normal formula for a hyperbola. A y value equal to something over an x value. Well, it's been tampered with a bit, but normally we have a constant here, and this is no longer a constant. It changes in value as x changes. But notice when x is worth 1, we get 1 minus 1, which makes this 0. So, when x is worth 1, we get 1 minus 1 is 0, and 4 times 0 is 0. On this side of the equation, to have a 0, we'd need y equals 1 as well. So 1 minus 1 makes 0, 1 minus 1 makes 0. So at y equals 1 and x equals 1, which is right here, something significant is going to happen. I hope you can see that that's purple and not black, because it's got to do with this. And that's why I like this divided and factorised form. Because when x is greater than 1, this is positive. And when x is less than 1, it's negative. That means on this side, when x is greater than 1, the graph behaves in one way, and on this side it behaves in an upside down way. Suddenly it's as though the constant on the top became negative. Well, that was a lot of chat to explain that, but let's see how it turns out. I'll actually graph it in purple. First of all, we have positive, 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 positive. So as long as x is a big positive number, we expect out here that it will behave like a hyperbola, if you like, in this top section of the graph here. So I'm just going to draw my graph there. When we come to this next panel, because these are normal asymptotes, I expect that we will have a corresponding part of the graph here. And sure enough, it will be asymptotic there, and it'll come up. Now, I know it goes through this point. I would expect it to come back down here, except for one thing. This business, when x is worth 1, remember this purple point here? It says that once I reach this point, the graph flips upside down. Instead of going down here, it's going to go up here. So this actually becomes a crossover point. The graph will go through 2 there, through 1, 1, and asymptotically up there instead of down. So the effect of having a linear function on the top is to see the graph flip, as it were, and we get a funny S shape take place. And now we can make sense of this point, because being normal asymptotes, we expect this part of the graph to be balanced by 1 on this side, diagonally across the crossover point of the asymptotes. And I expect one to come like this. We know the graph goes through there, and then it would have to go down here like that. So this is a slightly unusual graph. It's a bit hard to see this structure when we have it written in this form, but when it's in this form, this gives the game away that something is happening when x is worth 1. From that side to that side. So pay close attention to that, and you'll see this played out a little bit in the next couple of graphs as well. I hope that's made sense. Let's keep learning. Well, here we are with the next graph. This time I've stepped things up. We're looking at a cubic in both positions. Notice the same power in the numerator and denominator. That's why it's a type 2 rational function. And I think you can see that because this coefficient is 2 and this coefficient is 1, that y equals 2 is going to be our horizontal asymptote. Now, before we even do any serious calculation, we should be able to see that. But I would like to do the division, because I want to rearrange this into that other structure that I showed you. Now, to do the division, we've got x cubed and no x squareds and no x's minus 8. That's what this is. And remember, we need to keep the units column, the x and the x squared and the x cubed column. And we're going to divide it into 2x cubed. And no x squared and no x's and nothing. Well, x cubed into 2x cubed goes twice. So if I write twice this down, I get 2x cubes, no x squareds, twice that is no x's, and twice minus 8 is minus 16. Subtracting, 2x cubed minus 2x cubed is 0, which is what we expect, that's what we designed. Whole bunch of zeros here, producing nothing. And 0 minus minus 16 is plus 16. So that tells me that y is equal to 2 plus 16 over x cubed minus 8. I'm bringing the 2 over, and I've got 16 over. Now I'm going to factorise this. It is a cubic. 8 is equal to 2 cubed, so it's a difference between cubes. And it's going to be x minus 2 times x squared plus 2x plus 4. If you don't know how to factorise cubic expressions, that is the sum or difference between cubes, then please look it up in a book. I can't take time aside at the moment. Suffice to say that that is always going to be positive, but this one will change value. So let's analyse. We know that y equals 2 is our horizontal asymptote. We can see here that x equals 2 is also going to be an asymptote. Here it is here. Whoops, that's meant to be straight. Much easier to do on paper and certainly with a ruler. And because this can't be factorised in the real number system, it's not going to give us any asymptotes. So we have two normal asymptotes, nothing squared, nothing cubed. What about intercepts? Well, let's look up here. If x is equal to 0, x equals 0, x equals 0, we get 0 over negative 8, which is 0 for y. So the curve must go through there, through 0, 0. And that's obviously, if we substitute 0 for y, we get the same result. So that's the only information we get in terms of intercepts. Notice we have positive coefficient, positive coefficient, positive coefficient, positive number. So I would be expecting my graph to start up in this region, this neck of the woods. Being normal asymptotes, I would expect that I'd have a corresponding bit here. Because this is simply a constant, I don't expect there to be any changeover or change of sign, so I would simply expect to get a graph doing this. Now, it will be changed in shape slightly. Well, rather modestly actually, by this. Because you can appreciate that as x changes value, this is going to change value and influence the value of that fraction quite markedly actually. So it will distort the shape, but this is generally where the graph will be, and it will pass through 0, 0. I don't think there's anything else to discuss with this. It looked like a more complicated issue for us, being cubics, but it turned out to be actually a simpler rational function to graph than the last one. So let's keep travelling and see what is in store for us with the next equation. Well, here it is. Again, you can see if we expand this, we have a quadratic on the top, an x squared term and an x squared term on the bottom. The coefficient here is 2, the coefficient is 1, and 2 over 1 is 2, so y equals 2 would be our horizontal asymptote. Now we can confirm that by taking limits, but we can also confirm it by performing the division. And I'm going to perform that now. We've got x squared and no x's minus 4. And on the top, now I should have expanded this, x plus 1 all squared is x squared plus 2x plus 1. And let's double it. So I've got 2x squared plus 4x plus 2. X squared into 2x squared goes twice. So let's double this. 2x squared. Twice 0 is 0. And twice negative 4 is negative 8. Subtracting, that minus that is 0. This minus this is 4x. And this minus this, 2 minus negative 8 is 2 plus 8, which is 10. So what have we got? Y is worth 2. So that's confirmed our asymptote. And our remainder is 4 lots of x, sorry, I won't factorise just yet, plus 10 all over x squared minus 4. Subtract 2 from both sides. Now I'm going to factorise the top. I'm actually going to take 4 out. 4 times x is 4x plus 2.5. 4 times 2.5 is 10. And on the bottom, x minus 2 times x plus 2, because it's the difference between squares. So I've taken this expression, I've performed the division, and I now have this. Very, very useful. Let's go through the rest of our steps. We know the horizontal asymptote is y equals 2. Our vertical asymptotes will be at plus 2 and at minus 2. let's see what intercepts we get. Well, when x is worth 0, I get a negative 4 on the bottom, and I get a 1 squared times 2, which is just 2 on the top. 2 over negative 4 is minus a half. So when x is 0, minus a half. The curve must go through that point. When y is 0, I require a 0 on the top. And what value gives me a 0 on the top? X equals minus 1 does, or negative 1. Negative 1 plus 1 is 0. So at x equals negative 1, y is going to equal 0. Okay, well that's interesting. They're both in the same region. Going down to this graph, I'm going to ask the question about where we start our graph. Now, positive, positive, positive coefficients, positive coefficient, positive, well 4 is a coefficient as well. So I'm going to start up here. Well, I've got no other points lying around, so I'm going to draw that in there for the moment. Let's look at this expression though, because this does look like the form of an hyperbola, and normally we had a constant here, but here we can see this is going to change with x, and as long as x is bigger than negative 2.5, it'll be positive, because you can see that negative 2.5 plus 2.5 will become 0. So it's going to be positive when x is greater than negative 2.5, and it's going to be negative on the top if x is less than negative 2.5. And when x equals minus 2.5, we get a 0 here. To get a 0 over here, we'll need y equals 2. So by analysing this, we're finding the point on the asymptote where something important is going to happen. So y equals 2, so that's up 2, and x equals minus 2.5 is right there. Something is going to happen there. On this side, the graph's going to behave according to this. So down, etc., etc. We expect down and up. But once we get to this point, the graph is going to flip, because it's going to behave as though there's a negative index, a negative constant up there. Well, let's see what we get. There's another part of this part of the graph is here, so across these normal asymptotes I expect another bit here. Now it's not as symmetric as I thought it would be. I don't know whether I've made a miscalculation. Let's put x equals 0 again. No, I get 2 over negative 4, that's negative a half, so that's correct. And x equals minus 1, y equals 0. That looks right. So I must have a slightly lopsided form. Now, it doesn't, neither of these is necessarily a maximum or anything special, except that the curve goes through them. So I'll be expecting the curve would do this. I'm not drawing that very well. My gross motor skills aren't always the best here, but that's meant to be not quite touching the asymptote. Normal asymptotes here, so I expect the curve will be across here and coming down as well. Now, normally I would expect the curve to come out this way, but it's going to come down through that point and behave as though it's the remaining part of this curve down here. In other words, it's going to be, I'm going to have to move this, it's going to be asymptotic on the underside of y equals 2, and it will reach a minimum down here somewhere and do that. So I've got this funny little kink. Now to find the actual values here and the values here, we'd need to substitute or do some very, very serious calculus. To be honest, I think substitution might be a little bit easier. Just to calculate a few of the values. If you wanted to know the exact minimum and the exact maximum, then you know that you've got to do some calculus to find that, to find those points. But there's the basic shape for this particular rational function, type 2 function. Now I think I've written down a couple more to do. Yes, 2 more equations. So let's have a quick look at those. Well, we're drawing to the end, but we've got a rather interesting looking one here. You can see that the coefficients of x squared and x squared are 1, so y equals 1 is going to be our horizontal asymptote. And if you factorise this, x squared minus 1 is x plus 1 times x minus 1. So I'm going to have an asymptote at x equals 1 and x equals minus 1. And we can do that just by inspection. But let's perform our division and see what else is revealed. Actually, before we do the division, let's substitute x equals 0. So these all become 0, and y would equal minus 6 over minus 1, which is plus 6. There we go. Now that's interesting. I'm going to extend my asymptotes a little bit. What value of y would give 0? Well, sorry, if y is 0, what values of x? Well, to do that we would have to factorise. And this is x minus 3 times x plus 2. I may as well factorise the lot. You can see that we get x squared, and then plus 2x minus 3x is minus x, and minus 3 times plus 2 is minus 6. So if we want a 0 value for y, x equals 3 would give us 0, 3 minus 3. So x equals 3 and y equals 0, and x equals negative 2. Okay, so we did get some x-intercepts and a y-intercept. Now we'll get on with our division. We're dividing x squared and no x's and a minus 1 into x squared minus x minus 6. X squared into x squared goes once, so we just multiply this by 1, which means leave it alone. And we perform the subtraction. This minus this is 0. Minus x take away 0 x's is minus x. Minus 6 minus minus 1. Minus 6 plus 1 is minus 5. So y equals 1 with this remainder. Now I'm going to take the minus sign out the front. Minus x and minus 5. And it's divided by x squared minus 1. Bringing the 1 over with the y. And I'll get minus x plus 5 over, I'll put x plus 1, x minus 1. I'll just factorise that. Looking at this form, we can see that we have positive, positive, positive coefficients of x. Positive, we've got a minus sign at the front. So it says we're not starting up here, we're starting down here. And this point here confirms that for us, because we know the graph has to go through here. But we expect it to start in the negative region. So, actually before I draw it, we need to look at this point. You can see again, we don't have a constant on the top, we've got a linear function in x. And when x is worth minus 5 or negative 5, this is going to be worth 0. And on one side we're going to have one lot of values, negatives, and on the other side we're going to have positives. Now this particular expression here on the top with the minus sign at the front, as long as x is greater than negative 5, so where's negative 5? Down here, As long as x is up this side, we're going to have big values here, adding 5 positive with a minus at the front, so it's going to be negative. So it's as though we're going to graph this end as though we've got a negative constant on the top. But the instant we move beyond there to numbers less than -5, for example -6, we've got -6 plus 5 will be -1, with a minus on will be +1, we're actually going to get positive values. So down here it's going to behave as though the graph has got positive constant on the top. Where's the changeover point? The changeover point will occur when y is worth 1 and x is worth -5. So here it is again on, where's my purple pen, on the asymptote. So the line's going to cross the asymptote there, and something interesting is going to happen. Let's draw our graph. Well, as we expected, it's going to be in this quadrant here. Well, not a quadrant, but in this section of the curve of the graph. Normal asymptote, so we go diagonally across, and we're going to have an asymptote here. It looks to me like 6 is probably going to be the minimum value. So it looks like we've got a long, thin part of the curve down here and back up there. Diagonally across again, and the minus, this point here confirms it. I'm expecting the graph to do this. Now, it would expect to continue asymptotically below the line, just like this one was doing, except for this change of sign on the top at x equals -5. It's going to want to flip it so that it finishes off asymptotically above the line rather than below it. And the curve, in fact, is going to cross over. Oh dear, I'm going to see if I can draw this a bit better. I think this is going to come up here and rise up and then shrink, then bend down towards the asymptote again. And that's the shape of the curve. It's a little bit unusual. It's going to come up and then dive down towards the asymptote. A little bit unusual. We might not have seen that had we left the graph in this form. But putting it into this form, we're able to see this changeover very, very clearly. And that's what I want to encourage you to do. The division is most important. Well, I have one more, and just looking at it here, I tried to plan some out just a few minutes before I started, and I've chosen one with a little bit of an interesting twist for the last equation. So let's have a look at that one. Well, here it is. I hope you can see what's new. Not only is the denominator factorised, but we have one of the factors squared, which means we've got a double asymptote, which means we're going to see a little bit of a reflection take place. But let's continue. What's the coefficient of x cubed on the top? It's 1. And if we multiply this out, we get an x squared times an x is another x cubed. Y equals 1 is going to be our horizontal asymptote. Our vertical asymptotes will be at -2. And at +1. And I'll put, in the last video I was using red to mark the double asymptote, so I'll do that here. There we go. So we have a double asymptote at x equals 1. Let's find the intercepts. If x is 0, we get a 5 on the top. We get -1 squared, which is just 1, and we get 2. So 1 times 2 is 2. 5 divided by 2 is 2.5. So y will equal 2.5 when x is 0. So x equals 0, y equals 2, 2.5. Now, is there a value for y, is there a value of x that will give y equals 0? Well, the answer is there is one. You could treat this as the sum of two cubes. Now, 5 is not a pretty number. Well, it is normally, but not when you're dealing with cubes, it's not. So it could be x plus the cube root of 5 times, I don't want to get in here, but it'll be x squared minus cube root of 5x plus the cube root of 25. But we'll just, I suppose you should see it, shouldn't you? Cube root of 5 plus the cube root of 25, which is basically the cube root of 5 squared. Oh yes, I write the bottom. Now this, I don't think has any particular 0, but this one does when x is minus the cube root of 5. Now minus the cube root of 5, that's a little bit below 2, so it'll be in here somewhere. So minus the cube root of 5 will make 0 and y is 0. So I'm expecting, I'm just making a little bit of an estimate. We could write it in minus cube root of 5. You could find it on your calculator. The reason I know it's less than minus 2 is minus 2 cubed is minus 8. That will be fine. Okay, so we've got our intercepts. Let's do our division. Now to do our division, I need to expand this. This is going to be x squared minus 2x plus 1. This is just x plus 2. Let's multiply that out. This times this will give us x cubed. X squared times 2 will be 2x squared minus 2x squared. Well, that's handy. The x squareds disappear. Then we're going to have minus 2x times 2 is minus 4x, plus 1 is minus 3x, and 1 times 2 is 2. That's what I get. So we need to divide that into this. Let's have a look. X cubed, no x squareds, minus 3x plus 2. We're dividing it into x cubed, no x squareds, no x's, and a 5. X cubed into x cubed goes once, so we just multiply by 1, which means copy it out. That minus that is 0, that minus that is 0, that minus 3x is plus 3x, and 5 minus 2 is 3. And that's handy, we've got a common factor. So, we have y equals 1 with this. Now I'm going to take the 3 out as a common factor. 3 outside of x plus 1 over, I can write the denominator this way or the factorised form. I'll use the factorised form. And I subtract 1 from both sides. So it does involve a little bit of algebra, and you need to practice your algebra, practice expanding, practice dividing, practice factorising, all very, very important skills. Now what do I notice here? There are two things I'm looking for. One is I've got positive coefficients and a positive constant here, so I'm expecting my graph will start up in this region, in the positive area. That's the first thing I'm looking for. The second thing I'm looking for is that the top doesn't just have a constant, not just the 3. I have a linear function in x. And I can see here that this is going to be positive when x is greater than -1. Because -1 plus 1 will give us 0. And it's going to be negative when x is less than -1. Now if x equals -1, -1 plus 1, I get 0 here. And to get a 0 on this side, I'd need y equals 1. So we're after y equals 1, x equals -1. X equals -1, y equals 1. So something important, there's my purple pen, something important is going to happen here. It's a real mixture of black and purple. Okay, on this side, when x is greater than -1, it's going to behave as though we've got a positive constant on the top, which is what we expected. But once we cross this point, the thing is going to flip upside down. So we're going to get one of those squiggles or S-bends in the middle. I'll graph this one in purple. So we expect this to be here. Now I'd expect to go across here, but I notice I've got a red line on here, red dotted line or dashed line, to remind me that x equals 1 is a double asymptote, which means that instead of going diagonally across, it's going to act like a mirror image. So the two sides of the curve are going to go up either side of the asymptote there. Now this starts to make sense of these 3 points, doesn't it? Our curve is going to come down. Whoa, the board's moving and I'm moving. So please bear with me. There we go. That's meant to be, I think if I tamper with that, it's going to look even worse. So we've got an S-bend happening because we expected it would do this, but it's flipped over and it becomes asymptotic down this way. The crossover point is exactly where we expected. These are normal asymptotes here, so diagonally across we would expect to finish off the graph, like so. So there's the graph of this particular function. Now I've scribbled stuff in and around it. If I had a full sheet of paper, I would be able to set things out a little differently, but I'm rather restricted for room here, particularly with the graph taking half the screen. But what do I want you to observe? I want you to observe, first of all, that with these type 2 rational functions, that the horizontal asymptote still exists, but it's no longer the x-axis. That's different from type 1. The second thing is that finding the intercepts is exactly the same as with type 1. Finding the basic pattern is exactly the same as with type 1. But by factorising and getting it into this form, noticing what happens with this coefficient on the top, so not the coefficient, with the expression on the top, helps us to understand where the flip over point occurs. With type 1 it always occurred on the x-axis, but with these ones it always occurs on the asymptote. So as the asymptote moves, the crossover point moves with the asymptote. So this one's at -1, +1. So I want you to observe that. So the asymptote moves up and down, and also this crossover point, if one exists, will move up and down with it. And I think everything else should make good sense to you if you've seen all my past videos. So I'm not going to rabbit on anymore, pardon the expression. I would like you to leave your comments if you found this useful, or if you have constructive comments to make. Please like the video, and by all means subscribe so you find out about future videos. And I look forward to seeing you for the next video, the final one, where I look at type 3 rational functions. And as always, I thank you for watching.